Gauss's law summary. We first start by defining electric flux. Electric flux is represented by phi, and it's the strength of the electric field times the perpendicular area through which it passes. So if E is perpendicular to the area A, it is just E times A. The electric field lines represent a density, lines per perpendicular area, and that's the key here, this perpendicular word. Visually, they represent the flux. The more lines, the greater the flux through the area that they pass through. So for example, if you have an area and you have 3 lines passing through it, and in the same area you have 2 lines, this guy here represents a greater flux. So that's how you can see it. On the next slide, we'll tell you how to calculate it. We are not always interested in field lines that pass through a perpendicular area. They will pass through some areas and they're not perpendicular to it. So how do we calculate the electric flux? Let's look at this picture here. We have a perpendicular area represented A1 over there, and you can see the lines passing through it, and the way you calculate the flux there is just the strength of the electric field A times this area. So you can see that's what it is. However, how about this area? The slanted area. The flux is the same. Why? Just count the field lines. The perpendicular area here has 4 lines. This one has 4 lines. So you have the same flux going through both surfaces, but they have quite different areas. Now, just quickly, those flux lines don't really exist. That's our way to represent the strength of the field through the area. And by doing a little geometry, you find that the flux through this area is going to be E times its area cosine theta, and once you see something EA cosine theta, you have the dot product. So the flux for an electric field going through an arbitrary area is E dot A, or magnitude of E times the magnitude of A times cosine theta. And then if I have a surface that's not even or regular, and you have to do integration, you use this one. So the flux is the closed surface integral of the electric field dot dA. Gauss's law makes use of the electric flux, and it states that the electric flux through a closed surface, and we don't define it here on this slide, but closed surface is any surface that has an inside and an outside. The flux is proportional to the enclosed charge by that surface. So in solving problems, we choose a hypothetical surface, typically shown as a dashed line. Another name for that is Gaussian surface. And to calculate the electric field, we need the following criteria so we can apply Gauss's law. The electric field has to be constant at all points on the surface. Okay, that enables us to take electric field as a constant and remove it from the integral. The electric field is perpendicular to that surface. That enables us to reduce the dot product for the flux to just the magnitude of E times the magnitude of dA, the surface area vector, the little differential piece right over here. Or the electric field is parallel to the surface so that E dot A equals 0. This will help us make calculations. And let me emphasize right here. You can have a Gaussian surface where some parts of it, this is true, and the other parts of the surface, this will be true, and then you add them all together to get the electric field. Once you have chosen your Gaussian surface, you can now use Gauss's law, and you apply this closed surface integral over the entire surface of your Gaussian surface. The Gaussian surface has no physical meaning. It's just a mathematical tool, and it's chosen for its symmetry properties. Practice will help you choose the proper surface. There are certain very common symmetries that you should know how to do each one of them, or actually memorize them. They're not that hard to memorize, and that'll help you on the AP exam if you don't have to go looking it up. But if they ask you to derive it, hopefully by then you've practiced it several times, and that will also go quickly. We'll start with a sphere, and there's a different electric field inside than outside because you have a different enclosed charge. So here it is for anybody outside the sphere. Here's the electric field for inside the sphere. And all of these are for uniform distributions of charge, insulators. For example, if you have a spherical conductor, there is no electric field inside because there's no charge, right? There's no charge inside a conductor. For a rod, again, you have two answers for inside the rod and outside. And then you have an infinite plane, which is really kind of unique. This has no R dependence at all. It's a constant. Electric flux. We have a point charge, Q1, negative 4.2 nanocoulombs, is located on the x-axis at x equals 3 meters. And a second point charge, 7.6 nanocoulombs, is located on the y-axis at y equals 1 meter. What is the total electric flux due to two charges through a spherical surface of radius r equals 0.50 with its center at its origin? And then the next couple problems we're changing the radius of the spherical surface. That's it. And then, finally, does the total flux change when we increase the radius of the spherical surface from 4 meters to 6 meters, and explain.